Hello, everyone, and thank you for joining us today for Engineering Extravaganza Dream Team. My name is Danny Schroeder, and I'm honored to be your host today. I am joining you from Pennsylvania in the United States, and I work for Pannoni as a bridge engineer. The American Society of Civil Engineers, or ASCE, is partnering with the STAR Library Network, or STARnet, and its Project Build engineering program. Project Build is supported by the National Science Foundation. In addition to this Dream Team panel, we are providing free access to the award-winning documentary, Dream Big, Engineering Our World. Dream Big is available today on November 24th. The film is available in English, Spanish, closed captioning. To obtain a password for this opportunity, please visit www.asce.org/dream-big. Over the month of November, we have had several different dream teams. You can find the complete schedule and their recordings at the same website I mentioned above. The website is also posted in the chat for your convenience. So, before we get into all our activities for today, I want to talk about engineering. Computers, cars, tennis rackets, air conditioners, sports stadiums. Do you know who made all these things possible? Engineers. And while I've only mentioned a few things here, engineering is just about everywhere. An engineer is a person who designs and builds things to solve specific problems. And engineering is also a great outlet for the imagination as we use our creativity to help us with our designs. I'm a civil engineer, and one of my favorite parts about being a civil engineer is that we help communities through our problem solving and are building the world of tomorrow. Regardless of what problems we are trying to solve, there's a series of steps that engineers follow, and this process is called the engineering design process. I'm going to share my screen, and we're going to go through it step by step. Okay. So, as you can see on my screen, the first step is to identify or define the problem that you are trying to solve. Next is to learn the specifications. Here you can set goals of what the solution will accomplish. Another part of this includes building background knowledge on this problem. For example, location. If I'm building a bridge in California who rarely receives snow, there will be different specifications than in Minnesota, which sees snow way more often. Next is brainstorm solutions. Now, this is my favorite part. Here's where you utilize that creative problem solving to brainstorm a wide variety of possible solutions to the problem. This is the part where you really get to dream big about the many ways that you can go about solving a problem. Next, we go on to design it. This is the step where you get to draw. Here, you take one of your ideas from the brainstorming step and you show generally what it'll look like to help you with the next step, which is build it. Here, you can build a prototype or a model so that you can test out your design. This may be the most important step in the whole process, as engineers need to test out their design to see if it works the way they want it to. Then we get on to test, improve, and redesign. I also like to think of this step as the question everything, as this is where engineers test their design, review all the facts, and then ask themselves questions, followed by even more questions. What worked well? Why did it work? Why didn't it work? And how can we make it better? And most of the time, the answers to these questions are going to send you back. Now, notice here how these three steps form arrows that have a circular pattern. And that's because these are meant to be done many times. Chances are, when you get to this part, your prototype probably won't work exactly the way you want. At least, not on the first try. Most engineers test their prototypes over and over and over again, and you may even fail on the first try, and that's okay. You can learn from that failure of that test. You can design a new solution and then build it and then test it again until it works. And when it does work, you can continue to improve your product to make it even better. The last step is share it. Engineering takes teamwork, and we work with all kinds of people inside and outside the field to work together to find solutions. We also learn from each other, so by sharing your designs, it can also help others with their design, as they might be trying to solve the same problem in their local community. To summarize, the engineering design process is a series of steps that engineers or anyone can use when they're facing a challenge. Now that you know a bit more about engineers and the engineering design process, I will now hand it off to Sarah for the first activity.
Thanks, Danny. My name is Sarah McEwen, and I'm a water resource engineer in Jackson, Mississippi for AECOM. When you think of transportation, you may think of many different modes, but one mode of transportation we're going to talk about today is navigation and ports. So today's activity is taking foil and then designing a boat to handle a certain load, or pennies. And for me, this is really important because located in Mississippi, I'm very close to an important navigational waterway, the Mississippi River. The Mississippi River has several ports, which serves as a location where cargo can be transported from land to sea. So ports are very important in navigation and transporting goods that we need every day. And in order to meet the need, which would be to transport those goods, designers need to think about not only the river and the ability of that river to handle navigation and be deep enough for our boats, but how do the boats themselves handle the load that is being carried? So today's activity, our problem is to maximize the material provided, the aluminum foil, to design a boat that can handle a certain load. So to begin, you would take a piece of aluminum foil and fold it into the shape that you think could handle 20 pennies. And that's what we're going to test today. So I'll go ahead and show you our activity. So today I have 3 types of boats. I have boat 1, I have a sailboat, and I have a speedboat. So we're going to take each of these boats and we're going to place it in the water and we're going to insert the load of pennies and see which one can handle the best load. So first, the sailboat. So we will just start loading. We got 1 penny, 2 penny, 3 penny, 4 penny, and you can't really see, but there's already water and down it goes. So it only held 4 pennies. So I want you to think about, while we're loading the next boat, what was the reason that the speedboat didn't handle maybe the design process we were looking for? So next, the sailboat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, already more, 11, 12, 13, 14, oh, now it's failed. So now we're going to go with our flatter bottomed boat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and it failed. So looking at this, what were some concepts and why do you think certain boats handled the load better than others? One thing we think about is buoyancy, the ability of the boat to withstand and lift up against the pressure of the water. So one thing you could think when we were looking at a boat, think a barge, which typically transports cargo. Barges are long and flat and have the ability to sink with the load as well as handle larger loads. So take this example, take this design, think about what is your problem, what are you trying to solve? Our problem was cargo, so the flatter bottom boat seemed to work better. But if you're trying to go for speed, maybe the more angular design of the speedboat is appropriate. So engineers, as Danny mentioned, use the engineering design process to solve problems. This means we think about the problem, design a solution, test it, and try it again to see what works. So take this activity, apply it at home, and come up with your own theories and own things to test, and let us know how that goes. So now I'm going to pass it over to Brian for the next activity.
Perfect. Thank you, Sarah. So hello, everyone. Thank you guys for tuning in. My name is Brian Fan, and I'm a proud engineer for the Los Angeles Department of Transportation. I currently work on sustainable bike path projects for the city, but as an engineer, I wanted to know a very special project that I recently did specifically coordinating with COVID-19. As you guys know, we are in this pandemic right now, and it's still here to stay for a while. But when this first hit us back in early March, we didn't really know what to do, and we depended on healthcare professionals to really give us the guidance and protect us, and they are the true heroes in this pandemic. But as engineers, one thing that we do is we solve problems, and at the time, I felt hopeless. I didn't know what to do. But knowing that I had an engineering mentality, one of the biggest problems in America was the shortage of PPE, which is protective personal equipment. So, with the help of hundreds of engineers all over the world, we utilize our resources, which happen to be 3D printing. I'm a hobbyist myself. So I was able to find a 3D printing file of this face shield. This is probably the most popular face shield that this file has been distributed over probably millions of times all over the world. And this was shared throughout many engineers throughout the country. But here's the problem with this is even then using my own engineering design process to design this, there was many issues with this. Well, one of these took about an hour to print. Two, it took a very long time to manufacture and construct. And three, it just sat so close to the face. So with the engineering knowledge that I knew of, this was a big problem and I wanted to help more people. So I was able to redesign another one, realizing that these were my design constraints. And then I made a new frame. This is another one. It's much lighter. It sits farther away from the face to protect your eyes. And in addition, it only requires 3 connective tabs to hold the protective plastic film. The problem with this, still, it took about an hour to print this. So the other solution we had was to be able to stack them and to print multiple of them in one and then take them apart. So this reduced a 1-hour print to almost about a 20-minute print per face shield. From then, continually using the engineering design process, I probably prototyped over 100 versions of these in my garage. And ultimately, with this project, we were able to distribute over 5,000 face shields to hospitals all over California and throughout the West Coast. And in total, about 120 requests came through our website. So this was something that I just used as an engineer was able to figure out. Now, I just want to know, I didn't have, not all these skills were learned through colleges or universities, but I use the engineering design process just as you guys will when you guys solve your own problems, and thought critically and was able to find a solution for what is currently happening in COVID-19 right now. So with that being said, another problem that kind of arose was also some face ear savers that we were able to produce. So these were also very helpful, and this was redesigned as well. And now when hospitals use them, they basically put them on here and then they can connect them to the back of their neck like so, therefore saving the nurses ears in a sense. So this all comes down to my mentality as an engineer, but also the breakdown of the engineering design process. So I hope that was helpful and inspired you to solve a problem that you may have and that can help your community. All right. So with that being said, I'd like to also introduce our next part of our presentation, which is a video of the Falkirk wheel. Take it away.
Wasn't that neat? I'm going to now hand it over to Jaffer to talk about his activity.
Hi, everybody. Thank you for tuning in. My name is Jafar Al-Muswi. I live in Las Vegas, Nevada, and I'm a water wastewater engineer at GCW Engineering. So how many of you, when you woke up this morning, you brushed your teeth, went to the bathroom, took a shower? Hopefully everybody. But where does that water go? Especially now in COVID-19 with the pandemic, I'm sure you're all washing your hands multiple times a day. So how do we collect that water and how do we clean it so that we can use it again tomorrow? What I do is I build source systems that collect all this water and take it to the treatment plant for it to be cleaned. So an activity that you can probably do at home is make yourself what I call is a little mini source system. All you need are two, red cups and a straw, and you can connect more than, 2 or 3 of these cups together, pour some water in the end, and see if it comes out of the other end. Now, sometimes water will not flow because you have a flat slope. So what can you do? Using the engineering design process, you can change the slope by increasing the height of one cup and seeing how water flows. Does it flow better? Are you having leaks anywhere? Do you have to fix any of the pipes that are connected? Now what you can do is set up multiple of these cups, connect multiple straws together, and see if you can get your water to go from one point to the other point, and you can have that final cup be your treatment plant. So this is just a really quick, easy activity that you can do. I don't have water on me right now, or else it'd go all over my computer, but this is a very good activity to see how that engineering design process works, because sometimes we can't even get the water to a specific point without a proper slope. But in reality, you don't pour water into a cup and it doesn't flow through the top. So what does an actual manhole look like? So I have a little mini manhole here. This is probably what you've probably seen on your streets. So typically you're going to see a cover that goes on the top, and that's what you'll see from the ground. And then your pipes will come in through each side and come out through the other side. And that's what's really going on under your feet when you flush the toilet or wash your hands or anything. All the water is collected in that point. That's pretty much all I have. Try it at home. See if you can come up with a cool source system. It's not the most exciting thing in the world, but to me, it's very exciting because I'm cleaning water every day. So right now, I'd like to turn it over to the next activity, which is Danny.
Thanks, Jaffer. Okay, so for our last activity, I'm going to show you how to do the activity Slender Tower Challenge at home. So as we've heard from several engineers today and learned about a lot of different types of engineering and a lot of different awesome activities. For this activity, we're going to talk about a specific problem that structural engineers are solving right now. By definition, structural engineers are responsible for designing and constructing physical structures, including buildings. And because of advances in technologies and materials, we are able to imagine and design skyscrapers that are larger than ever before. However, cities are already filled with buildings, so we have limited space to build these skyscrapers, so they need to build up instead of out, hence the slenderness of most skyscrapers. So for you to do this activity at home, you'll need 10 sheets of paper, scrap paper if you have it, scissors, and a roll of tape. Your task or challenge is to build the tallest tower with the smallest footprint you can with those materials. So let's look at my example base here. So this is the footprint. As you can see, what is going to be the interaction with either your floor or your table is your footprint. And as shown in my model, an important part of any tower is a sturdy base or foundation, because that helps the slender tower to keep its balance. And skyscrapers work in a similar way. Having a base that is firmly attached to the earth helps support tall buildings, even when they get pushed around by wind, storms, and even earthquakes. Another way to imagine this is when you stand on your 2 feet. Is it easy or hard to balance? Now think about it with only balancing on one of your feet. Does it make it easier or harder to balance? It should be harder to balance because now you have a smaller area or footprint that is supporting you, which is why the base is so important to your design. The more stable your base, the taller your tower can be without toppling under the load. Now, going back to the engineering design process that I talked about in the beginning, this was the first base I designed. And then, although it works, it used 3 full sheets of paper to make. And when my specifications say I only have 10 sheets, this is a lot of paper to use just for my base. So after testing this one and getting it to work, I wanted to improve my design. One thing I also want to notice about this is that I had a triangular base, and then I had tubes supporting a central tube because I wanted to be able to, for the rest of my tower, mainly just use tubes to make my tower go up. So here is my second design, and hopefully I can turn this down without hitting the wall. So this is my base now. It's also a triangular base, but much smaller. So I was able to redo my base and improve my design. So I was able to keep that triangular base shape like my original design, but with a much smaller footprint that used less paper. So this was only 1 piece of paper now, as opposed to 3 sheets before. And hard to tell, but this tower is about as tall as me now, so a little bit over 5 feet. Also wanted to talk about the connections here. So as I talked about, my triangular base, and then the main of this was to be a tube. So what I ended up doing for the connections is I took my tube that I want to connect it with and made slits in my piece of paper. Sorry, it's a little hard to see, but I cut slits in it, and 3 slits so that it could go on each side, so that I was able to have a connection on each side of this triangle to my next piece of my tower. So if you try this activity at home, once you have a successful tower, you should try it again with the goal of either making a taller one with the same footprint or making it the same height, but with a smaller footprint. You can also experiment with different types of paper like cardstock or construction paper. And that's it for the activity. So we are now going to go into questions. So we're going to start answering some of the questions that you've had so far. If you haven't asked the question yet, this is a perfect time to add it in the chat. The first question that we're going to start with is, when did you start thinking that you could be an engineer? Brian, do you want to take that first?
Yeah, that's a great question, because I'm going to answer this really uniquely, because I did not decide that I wanted to be an engineer until late high school, junior, senior year. And that's the big question. Everyone's like, hey, what am I going to major in when I go to college, and so on. But I came about that because, one, I started thinking, what did I like to do? And I remember when I was a kid, I'd like to take apart things, a lot of things. So if you gave me a screwdriver, there'd be probably something laying around the house that was just in shambles and in pieces. So that's what I did. And I slowly reflected and saw what I like to do and how that incorporated into my career. So and then I was like, all right, let's try this out. I'm gonna try to be an engineer. And this wasn't even the thought that, was I good at math? My math grades were okay. Was I good in critical thinking? That was okay. But I knew that I could try to take things apart, figure out a problem, and solve it. And lo and behold, after going to college at Cal State LA for engineering, here I am as a civil engineer for the city of Los Angeles.
Awesome. Jaffer, would you like to also add a little bit about your story?
Yeah, so as a kid, I never knew what I enjoyed doing. I knew I was really good at math, and one of the toys that I always played with was Legos. And I'm sure everybody knows what Legos are, and I honestly, to this day, I still play with Legos. And I always built my own structures, my own buildings, and I could spend hours doing that. And when it came time to choose my my major in college, what better choice than to go into something where I'm building something constantly. So I think that's the main reason why I got into civil engineering. I didn't know that I would end up doing water, but at the same time, I enjoy that aspect, that I'm still able to build something even though it's underground and not above the ground.
Awesome. Before we go into more questions, I just want to talk about one quick thing that Brian mentioned of that he wasn't the best at math. And that's something that we hear a lot about engineering of, oh, I need to be so good at math and science to become an engineer. You need to like them because they will be part of your job, but you do not need to be the best in those subjects. It's if you really love that problem solving, this is an excellent choice for you. And similar to Joffer, I also played with Legos when I grew up. I'm a bridge engineer now, so Legos are really awesome in the fact of, especially the little Lego blocks, you need a lot of little Lego blocks to make that big structure, and that's kind of what I do with bridges now. It's a lot of different pieces that come together to make that full structure, which is really cool. Okay, on to our next question. What did your parents think when you were deciding to be an engineer? Were there any other family members that supported you? Sarah, can you start with this one?
Yes, and it's a bit of a joke in our family that you pretty much only could be either a calculus teacher or an engineer. So I was very fortunate in that both my parents are engineers. My mom works for Marshall Space Flight Center, and my dad also works for Marshall Space Flight Center through a consultant firm. And they've both been my dad's mechanical, my mom's computer engineering, and they supported me wholeheartedly, even though I chose a slightly different engineering curriculum than they did. My sister's biomedical engineering. We have cousins and uncles who are chemical and all different agricultural. My husband's civil engineering also. So it really wasn't a choice for our family. It was almost kind of like you grew up with those conversations and that mythology and that application. So whether it's cutting the grass to, changing a light bulb, our family was always like, well, what's the most efficient way that you could do this activity? And I think it drives some people in our family crazy that we have that thought process and interact with that way. So I was very fortunate to have not only, a female engineer to look up to in my mother, but a lot of strong engineers to support and instill those design processes from a very young age.
That is awesome. Another thing that you touched on is we are all civil engineers on this call, but there are so many types of engineers out there, mechanical, chemical, just to name a few. So there are a lot of other engineering fields within, even though we are all just talking about civil engineering. So the first question that we have from the chat is, what is one of the favorite projects that you have worked on? I will answer this while you guys all think about your answers. My favorite is the Burlington-Bristol Bridge. It is a vertical lift bridge, so it moves up and down like an elevator. And this is my favorite project because I've gotten to see it through the design part, but also the construction. This bridge has been out. I should mention, I didn't design this bridge. This bridge needed to be repainted, so we needed to add retrofit plates or something to strengthen the bridge so that it could be painted. So I got to help. I designed the plates for this retrofit and then also followed up and got to be there throughout the construction process to make sure that what I designed actually goes out into the field.
I guess I'll go next. A project that I worked on that was probably one of my favorite was a fish passage. So we were doing a bridge hydraulic replacement and we had a severe drop at the outfall of our culvert. It was about a 10-foot drop. So if you think about some small fish, a fish is not going to be able to overcome that 10-foot drop. So we had to design not only new channel that reduced that drop and sloped slowly, but we had to make sure that we had a step pull system so the fish, within its allowable ability to kind of jump upstream could pass upstream. And this was, one of the first that was designed in the Southeast, and there were no, available guidelines. So we did a lot of research into, what is the capabilities, the biological capabilities of the fish, but this was uncharted territory. How do we consult with the Fish and Wildlife? How do we consult that's something that's actually constructible and buildable that could be maintained? So it was very challenging and just an opportunity to do research, which I'm, a problem solver, and this was something to just kind of run with that I thought was really cool.
Awesome. Jaffer or Brian, before we move on, did you want to talk about projects really quickly?
Okay.
I'm sure you're both working on awesome projects. So we'll go on to our next question. Have you ever given up on a project? So for me, I have not given up on a project, but there's definitely been times where there's been bumps in the road, as I will call it. So for example, of a project I'm working on right now, we're doing a reconstruction of a bridge, and underneath the bridge, they're putting in a trail. And there's a lot of specifications of what we want for that trail. So we're running into a lot of challenges of how wide you want it to be under there, the lighting, lots of different things that go into the trail part that definitely are difficult and require a lot of coordination, both with people that are engineers, but also not engineers, to get this project to construction. But lots of challenges that we go through. But again, we are working as a team to get these solutions. So it does take time, but you can get there and you can overcome any challenges that come your way.
Yeah, I can chime in on that as far as giving up on a project. So on a day-to-day job, we work on tons of projects and different scopes and stuff like that. But one of the projects that I did work on happens to correlate with both cyclists as well as equestrians. So the goal, plain and simple, was we were trying to get cyclists from point A to point B, and there were many roadblocks in the way. We couldn't squeeze a path that was fitting the right of way. We couldn't make sure that they could get there safely. So frankly, I'll say, yeah, we did give up on that option because it wasn't a feasible option. But I want to say give up because we had to reinvent what the problem was. And ultimately, the problem was how can we get both the horses and the cyclists to use this path to be shared together. So rather than abandoning that, we went back to the drawing board and had to revise what the whole prompt was and what the question was, and ultimately came up with a solution where both we were able to utilize the space for both equestrians and cyclists. So you win both there. You weren't really to solve the main problem. So yeah, we did give up on that one, but then we ultimately solved a bigger problem which helped both communities. So.
Yeah, I would just add, sometimes it's not giving up on the project, but it's facing either the realities of your constraints and expressing those to the client, whoever that is. And sometimes that's a hard conversation. It's hard to tell someone who may have something really in mind that, the realities of whether it's budget, scope, or anything can maybe, keep your idea of what you want done kind of to a different scale. Or sometimes you have to have the really tough conversation of, this isn't in the best interest of the environment or the best interest of the community, or it's not following federal regulations. So it's not so much giving up on a project for me, but maybe kind of like Brian said, changing the trajectory to fit not only the service of the client, but the better service of the world.
Awesome. And I wanted to say thank you, Hannah, for that question. We're going to go on to the next question from Reem. Is it hard to be an engineer?
I can answer that one. Anything is hard if you don't put in the effort. I think with engineering, it's definitely not easy. But what you're taught is you're taught to learn, use your resources, ask questions, reach out to people, because you're not going to know every single problem that you're presented with. When you're going through school, you're taught, how to, solve problems, but you're given a information that helps you get to a solution. And in the real world, it's not like that. There's never going to be an easy solution. So yeah, it can be hard to be an engineer, but there are a lot of people out there that are willing to help that you can reach out to. There's a bunch of resources that you can use. And yeah, it's only hard if you make it hard on yourself.
Yeah, I just want to echo on what Jaffer said. As the biggest struggles of one thing like you guys may consider is like taking engineering courses in college. Engineering degree is not an easy feat, but Every class is so rewarding. And, one may think, I always tell students this, like, hey, you guys are going through school, you're learning all this math, calculus, physics, science, and stuff like that. It trains you, it shapes your mind, it shapes your brain, so you start seeing things differently. So sure, I may not be using physics problems on my day-to-day job, but I now look at any problem and able to apply math and logistics and physics to that. So it was hard at first, but eventually things just started clicking. And as your brain and you shape that mentality, it grows and grows and grows. It only gets better as you develop and work at it. So yeah, definitely great points there, Jaffer.
And I think this also circles back to when Sarah was talking about family, of also being with a family of lots of different engineers, using that engineering design process beyond your projects, of breaking down a problem. And even if you have an answer to the problem, how can you make it more efficient? How can I do this quicker, faster, for cheaper, with still solving the problem that's at hand? The next question we have is from RM. Any role models or inspirations that stick out that helped shape your career trajectory? If not, I can take this really quickly first. So my inspiration from the historical side is Emily Roebling, if any of you have heard of her. So her husband was originally her father was originally in part of the construction of the Brooklyn Bridge. And then unfortunately, he got sick. And then her husband took over taking over the construction of the Brooklyn Bridge. And then unfortunately, he got sick. So she ended up seeing the rest of the construction through of the Brooklyn Bridge. And there's pictures, if you Google Emily Roebling, of her in the clothing of the time, so like a very large petticoat dress on the Brooklyn Bridge as it was being when it was being opened to vehicular, or in that time, I would think it would be horses and buggies and pedestrians at that time. Does anyone else want to talk about a role model or inspirations?
I would say maybe not an engineer, but I had, several high school teachers. Mr. Chambers was one of them, and he taught theory of knowledge, and it was a weird class that our high school had to take, but it really just taught you how to think and how to think critically. And I think he inspired a lot of us in that grade just to, not limit ourselves by what we're told we can be or can't be, but, to apply critical thinking and just absorption of knowledge. You may not have to agree with everything that you read or understand or, are told, but, take it in and think about it and say, well, I can understand how someone else, came to that conclusion or that philosophy. I mean, that's the evolution of philosophy from the beginning of time, was people changing their minds about how we interacted as a society. So I would say him and then my other teachers at the International Baccalaureate School were really instrumental, and I think a lot of people's career of just pursuing what they can do, not necessarily what they're told to do.
Awesome. So we will go on to our next question of, what are your favorite activities to do outside of work? Jaffer, could you answer this one first?
Sure. Right now, it's a little hard to do a lot of things outside of work, considering we're in a pandemic. But typically, I love to travel. I love to visit a bunch of different places all over the country, even out of the country. I enjoy. I love movies. I go to the movie theater a lot. I go to concerts, hiking, working out, basketball. As much as I can do, I'm doing it right now. The one thing that I am doing a lot is Netflix and actually Legos. So that's pretty much what I've been using a lot of my time for right now.
Awesome. I think I can echo on what Jaffer did too. I think we're very like-minded individuals, but I love outdoors. I love camping. I love going out. So one of my biggest hobbies right now is I'm actually building a overland truck vehicle, so I can go camping and disperse camping and so on like that. So it's a big project of me. I've always been really into cars. So whether it is installing suspension, modifying things within my car, messing with the head unit. Right now, I'm working on building a custom roof rack for my car, and using engineering, actually. I have structural calculations to be able to determine how much load I can put on there, and so on. So that's been a huge hobby of me, and it's been fun, and where I'm able to incorporate a lot of things I know in engineering and something I do as a pastime recreational, just to enjoy life. So that's something that keeps me busy.
I would say for me, I enjoy reading. I really enjoy cooking. And I think we've all gotten to do a lot more cooking at home lately, and that's probably good for everybody's budget. I made cinnamon rolls for my family, so that was kind of a fun activity. I kept texting my friend asking if does this look right? Is this going in the right direction? So I'd say cooking and reading. Like I did run a half marathon this year before the pandemic, so I probably need to get back into running since that's a good single activity to do during all of this.
Awesome. And I think this also emphasizes that beyond engineering, you can still have passions and hobbies that outside of work that you can still continue and enjoy. Sometimes they even do relate to the engineering side of it, as Brian kind of talked about with his hobby of 3D printing before and how that was able to solve a problem. And it looks like we're almost out of time. So I would like to take the time now to thank our three amazing panelists. Thank you, Sarah, Brian, and Jaffer, for all that you do and for sharing your passion for engineering today. And then we're going to bring up some closing slides. So thank you all for joining us today. We hope that you enjoyed this presentation. If you are watching live, please take a moment to fill out the 5 short questions on our feedback form, which the website is on your screen right now, which will help us to plan for future events. Your responses to this will be anonymous. And then I think the link will also be added to the chat so that you can click it that way. And then on to our next slide, we're going to show a few activities. So some of the activities we talked about today: foil boats, Slender Tower Challenge. There's a link on this slide to show you where you can get more information about these activities to help you to develop as an engineer. And that is all we have for today. So thank you so much for attending. Bye.
Awesome. Thank you so much for having us. Great panels, great event.